you very much. I'm excited to be here. My name is Edward Kim. I'm from Villanova University. This work was done with my collaborators, Ed Lawson, Keith Sullivan at the Naval Research Labs, as well as Garrett Kenyon out in Los Alamos. I'll talk about, spatial-temporal sequence memory for prediction using deep sparse coding. I'll first talk about this idea of why we're doing prediction. I'll go into a brief introduction to deep sparse coding, and then finally spatial temporal sequence memory. I'm going to make my own predictions. Right now I have two. One is I'm not going to stay on time. I'm sorry about that. I'll try my best. The second I'll do at the end of my talk, so stay tuned for that. Okay, so why are we doing this task of prediction? Well, many people say the brain is an advanced prediction machine. Jeff Hawkins, well known in this community, says on his book on intelligence, prediction is intelligence framed by understanding. Carl Friston's a neuroscientist, says the brain is doing active inference and predictive coding. Predictive coding is this idea that perception is a combination of both input and as well as some sort of top-down expectation or prediction, modulating that input. And then even, I know that oftentimes neuro-inspired and deep learning, we don't agree on many things, but even in the deep learning community, I think there's this idea that prediction is paramount here. Prediction is the essence of intelligence, is Jan LaCuna. Okay, so prediction, it happens in multiple places in the brain. It's not just in sort of one area. And what we're going to look at is this idea. So they did a study. They showed that in the mouse visual system, neurons in the low level became predictive over time. All right. Okay, so sparse coding. So Mike Davies did a very good introduction this morning. So I'll go quickly in this idea of what we're doing with sparse coding. So basically, we have a reconstruction task. Okay, so we have some input, so some input image. And all we're going to try to do is reconstruct that input image. This is an unsupervised task. And we'll do this, we'll take maybe image patches here and try to reconstruct that using, so this phi term, this is going to be our dictionary. And then this TU is going to be the activations of that dictionary. Okay, so just to spoil things a little bit, this T is a thresholded of the membrane potentials U. Okay, so what does this phi look like? All right, so this is the dictionary. This is learned from the data. And you can see that it becomes sort of these, it sort of captures the structural primitives of, in this case, natural world scenes. They become these sort of edge detectors. And so oftentimes we'll say that these are also the generators of the data. And then so if we have this input patch here, we can then start to think about, okay, maybe I can reconstruct this using a little bit of this element, a little bit of that, and put them all together. Okay, so that's how we're going to do our reconstruction. All right, so then we sort of take a step back and then we say, well, if I'm going to reconstruct this image, what I'm going to do is I'm going to minimize this energy term. So we're going to do the original image minus the reconstruction, sort of squared error here. But we're going to also care about sparsity. Okay, so we don't want the activations to be very dense. We actually want to penalize the sort of dense activation. So we want this to be sparse. And so I'm going to sort of take this idea of sparse coding and put it into this visual representation here where I have I as the input image. I prime is going to be the reconstruction, and then this TU, this activation, I'll call this V1, right, just to confuse things a little bit. I'll call this V1. Times, or using this dictionary, I can then sort of reconstruct that input image. All right, so that's sort of the idea of sparse coding. We're going to use a biologically inspired solver for this. It's a dynamical system. It's called LCA by Rosell. And I should mention that we're using my collaborator's software called OpenPV from Los Alamos. It's on GitHub. It's publicly available. And so we're using sort of this modified LCA that the neurons of the network can be thought of as leaky integrators driven by the input image. We're introducing a term lateral inhibition. So now we have connections within the layers. These neurons are going to be inhibited by other neurons that look sort of like them. And then we'll say that the dictionary learning here is through Hebbian-like rules. Okay, so It's going to use the residual of the reconstruction here, and then and the transpose of the dictionary to learn these dictionary elements. All right, so now moving down to deep sparse. Why are we going deep? Well, we know that there are hierarchies within the brain. We know that deep learning has had some good success sort of looking at compositional elements. And so we're going to do the same thing. We're going to I'm going to take this sort of one layer sparse coding, sort of just bend it, all right? You call this D1. And then we're going to put another layer of sparse coding on top of V1, call this V2. And what this is doing, it's doing the reconstruction here of the membrane potential of V1. So that would be sort of the reconstruction. It's going to learn its own dictionary D2. Now, the idea here is that V2, it has its own dictionary. It's trying to reconstruct V1, but it will have some sort of reconstruction error as well when trying to reconstruct V1. And that error, it's going to be pushed down to V1. So in the next time step, when V1 tries to reconstruct the input, it's being modulated both by the input signal as well as the error coming down from V2. So it's sort of like a top-down feedback. And then we can say, well, we can then go from V2 back to V1. The reconstructions is actually the same thing. And then we can go to reconstruct the actual input from there. And I'll sort of abstract all these details away and just have this be the sort of the representation, just to make sort of things a little bit easier. All right, so if this is sort of deep sparse coding, you can imagine we can stack multiple layers here. We can also go wide. So we'll go deep and wide here. And this is what we've been doing. We've been adding, I guess you could call it different modalities to the network. So not only are we trying to sort of reconstruct like an image input, you can think of maybe this is like a stereo pair, where now we're going to try to reconstruct the other side of the other modality as well, and if we sort of train this together, we're going to use sort of these linked dictionaries. So D1, D2 here become linked, and we've been able to sort of modify this architecture. We don't have to stay with similar sort of image-image pairs. We can go image-audio and that sort of thing. And when you do something like this, these are trained together, D1, D2 become linked. You can do things like this. So you can take away the audio input, for example, and say, given an image of a cat, I go through this network, and so this V1 layer should then be able to capture both the activity of I1 and the missing I2, and it comes through here, and then you can sort of do sort of this modality translation operation where I can show an image of a cat and then have the network say cat, right, at sort of test time. All right, so how does this sort of translate to this idea of spatiotemporal sequence memories? Well, you don't have to stop at 2. We just sort of keep going. So here we have 5. And so now we're going to say, well, these are similar modalities. These are actually going to be frames of an image. We have 5 frames. If we train a network, this deep sparse coding network here, these D1 through D5 dictionaries also become linked. All right, so how do we use this for predictive power here? Well, in the same way, then sort of at test time here, we would say, well, we'll just show the network 4 input images. And because D1, D2, these are both spatial and temporally linked here, then we can sort of hallucinate or reconstruct the next time step of a video sequence just by using these D1 through D5 linked dictionaries. All right, so we've done this on synthetic data. We've done it on realistic data. So here at the Naval Research Labs, they have these highly reconfigurable areas. So they have like industrial centers. They have an indoor rainforest. You can actually make it rain in there. They also have a desert scene. I'll show you that in a little bit. So we were doing some predictive sparse coding here. And what I'm just showing you here, this is just the video. These actually have no time correlation to each other. This is just the evolution of one dictionary element over time. So in the beginning, it's just sort of random. And then as it trains, you can see like structural primitives start coming out of the dictionary. So these sort of edge detectors here. Now, if we look again, there's no time correlation here, but if we look at a snapshot in time and we see this video is going to play, this is going to be the 5 frames of the dictionary. You can see these are what we're calling our spatial and temporal sequence memories, where in fact, they become, so some of them are stationary, but most of them become for these moving edges. Okay, so if you look at synthetic data, you don't get edges. You get, if all it looks at is bouncing balls, it learns bouncing balls. All right, so this is what we've been doing. So here's an example here of, up top, we have the ground truth. So this is the actual 5th frame. This is the hallucinated, reconstructed 5th frames of an image sequence, and this is in the desert scene, the NRL. And here is just another example of hallucinating the future. Okay, so here's my second prediction. And so we've been working with Intel on the low EE processor. So they've shown very good, very promising results on this problem of solving lasso LCA. I think the numbers were like 1 million times less than out of time. Okay, but anyway, so my prediction is that we're going to be doing this in the future on the low EE chip. I think that's a good direction to go with the low power and high processing. All right, so that's my second prediction there. We have shown the ability to hallucinate the future, and we can quantify this prediction error, use that for learning, use that for anomaly detection. And I think one of the things I want to highlight is we're just using reconstruction and unsupervised reconstruction to do things like modality translation, predicting the future, classification, all that. It's all coming from just reconstruction objective function. All right. So I'd like to thank some of my funders, and we have no time for questions. So thank you.
Thank you, Ed.